from your perspective, what was the most critical innovation in the Curiosity or Perseverance EDL system?
Well, in Curiosity was the sky crane,
Hmm.
that method of landing um, that we have to invent, right, to land a
Yeah.
almost 1 ton rover on Mars. We um, we have done airbags before that in Pathfinder and MER rovers, Mars exploration rovers, and then Viking was a legged lander. But and then Phoenix and was a legged lander, but we couldn't figure out a way of landing such a big rover on a legged lander because in a legged lander you have all the propulsion system below you, so then you have the legs, so then all of a sudden you get your rover like a meter or so over the surface and trying to get it down on Mars is not a trivial task. So we decided to put the propulsion system above the rover, and
Yeah.
lower it,
Okay.
which is in some ways not that different in retrospect. I don't think that we were thinking that way, but having worked with the airbag landers, the engines were also we have uh, solid rockets to slow down. They were very impulsive. It was solid rocket, so they're 2 or 3 seconds duration that would fire from above, right? So
Okay.
this was an extension of that idea. So that was, I think, the most innovative thing is to essentially land it like it was a helicopter with a cargo on the bottom.
So, was that like a hard sell initially, or
Yes.
so it was hard, or did the data kind of speak for itself there, and really it really kind of showed how certain it was to actually happen?
Well, actually, that whenever we expose the idea, we have two responses, right? Either genius
Mm.
or you are crazy. That's the silly idea. That's too risky. And I had arguments about it, with people that are very experienced and knowledgeable about space systems until the day before we landed, right? And so, so when we show this to our boss, I mean, the project manager, Pete Teisinger,
Mhm.
was like, "Whoa, I said I had to convene a panel of experts to go
Yeah.
through this and give me the green light. Otherwise, he just couldn't do it, right? So he convened a panel he asked the Aerospace Corporation, which is a think tank, advisory type of institution to mostly the military service. I think it's the Air Force. He asked them to convene a board made out of experts in the fields of landing, including an engineer that designed the landing legs for the lunar module.
Okay.
But then he has a helicopter pilot, and he had a person that walked on the moon, Jack Smith, as a member of this board, and other people with a lot of experience. And so we had to expose to them, I think it was a couple of times, full days, or at least 2 full days, I think, of presentations, and by the way, the person that landed that worked on Apollo immediately got it, and he gave us the green light. I said, absolutely, that's the right way to do it. And eventually, there was kind of like a voting at the end, and everybody agreed that was the right thing. So then our project, the project manager, approved using that, and then a team of JPL had to go to Washington, D.C. to try to convince the NASA administrator, right? So, yeah, it was a hard sell because it was really, people were very concerned that this pendulum, with the rockets on top and the hanging payload, that was going to be unstable. But we felt, coming from working on airbag systems is the opposite. They looked very simple, right? Because what could be simpler than like something that bounces, with like a balloon, right? But the physics, the modeling of that system was extremely complex because you had to model this, soft system, which is an airbag, interacting with different velocities with a surface that you don't know. So it could be rocks of every single size. So the modeling of that system was a nightmare. So it was purely empirical. We tried it on Earth with different, in a vacuum chamber of different sizes of rocks. And we kept fixing it because the airbag kept blowing up until we felt that it was safe enough. But the sky crane, on the other hand, the modeling of the sky crane was very simple, right? I mean, Galileo Galilei discovered the pendulum many centuries ago,
Yeah.
right? So we knew that we could model it. If you can model it, then you can control it. If you can control it, you feel really safe on landing day. So for me, and for a lot of people that worked on it, we actually were very confident to the point that we never tested it on Earth. The first time we used it was on Mars. We saved the money of doing an super expensive test that it would have been pretty much an F equal MA test, we call it. A test that is pretty obvious what the result is, so you don't learn anything. So that was the level of confidence we had on the system that we didn't test it on Earth. We tested on Mars for the first time.
So, for the sky crane development, was there something super, super unknown that worried you the most?
No, I mean um, it was pretty straightforward, to be honest. It was just straightforward engineering. We had a little bit of a realization very early on, which is,
Yeah.
when you can handle it.
Well,
That
did you have to test or simulate anything on Earth?
Oh yes, yes, yeah. You do. You don't test the full system like with the
Yeah, of course.
rockets, the bridle, But but in exchange for not doing that, every component, right, that makes the system is tested, right? So for example, there is a brake. You don't just let it fall 7 meters, right? It goes,
Yeah.
and that was actually a pretty clever trick. We wanted to make it as simple as possible, right? So it was passive. So there was no computers. It was pretty much like the way the regenerative braking works in electric cars. In
Okay.
electric cars, when you remove the foot from the pedal, they slow down because the motor acts as a generator, right? And then it creates, then there's a load. In the case of a motor, is the battery that you're recharging the battery. In our case, was a bank of resistors
Mhm.
that where the what's called the back EMF, which is like when the motor operates as a generator, creates a voltage, and then if you put a load like resistors in our case, that creates a current, and the current is going to generate a torque that opposes the motion, is the Lenz law, right? So 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 that system that slow us down, and you can change the rate of descent by changing the resistors values, which was very, very simple, thing to do. That was tested, a standalone, right? By pulling on it. Then we tested the bridles, right? We need to understand the elasticity. We wanted the bridles could not be too soft, but also could not be too stiff. If they were too stiff, then the system would be unstable. So we specify a range of flexibility, right, that can be handled by our control system. So that was very well understood. So now we needed to make sure that that range of elasticity was respected in conditions of vacuum and different temperatures. So there was a lot of testing on the bridles, right? And then the engines, the operation of the engines, we did all sorts of tests of a single engine mounted on the test stand, and to, for example, understand the frequency response of that engine, right? Because we need a high bandwidth so the system, when it came down, it will quickly settle, right? So each component was thoroughly tested,
Okay.
right? And then we came out with mathematical models of each component, and then we put in a big simulation and then a Monte Carlo simulation, which is a way of doing statistical variations, right? And we proved that the system worked on simulations, right? but simulations using mathematical models of that were validated with experimentations, for each component.
So terrain relative navigation was huge for Perseverance, obviously. What
Correct.
was the hardest part of getting it to work reliably?
Well, yes, you're absolutely right. That was the delta, right? The innovation in Perseverance. Perseverance was pretty much the same as Curiosity, but
Yeah.
we add terrain relative navigation, which allowed us, while in previous missions we have to always find a landing, our landing ellipse is not, we cannot land on a dime. So we have a certain area of uncertainty, right? Which we've been making it smaller and smaller, right? So in Curiosity, another thing that we did was entry guidance, right? Allowed us to reduce, because before it was a ballistic entry, essentially. We landed where we landed. With Curiosity, we put the Apollo entry guidance system where we flew the spacecraft with an angle of attack, so then it behaves almost like a wing, right? So we can fly, we reduce the landing ellipse, so we can actually go to, for example, to the place where we was a crater. We're landing inside a crater, right? Between a crater and the mountain in the center of the crater. But that area of landing had to be really safe in terms of slopes and rocks, right? So then you land here and your science is outside. Usually the science is outside the ellipse, right? The problem is interesting science, requires topographic terrain that is usually not very conductive. It's dangerous for landing
Yeah.
purposes because you want to be exposed, strata, like and rocks themselves, right? That's where the information is, right? So with TRN, it allowed us now to pick a place to land on the science, essentially, right? And like, for example, the Jezero crater that they targeted, there was this beautiful, interesting, scientifically interesting delta with very large carbs. So they're very dangerous, right? But the science was right there. So then with TRN allow us to be able to land there because once, by determining where you are, then you can figure out where are the safe sites. In terms of the, the challenges there, right, it's you need to get the right map. There are several challenges. One is to get the right map, right? Because essentially you need to predict what Mars is going to look the day of landing with the current illumination, right?
Yeah.
So that was a big challenge. Obviously, the system had to operate very fast, right? Because you don't, entry, descent, and land is very quick. Boom, boom. So you need 10 seconds to come up with an answer. Okay. So then they needed to design, the TRN team had to design a computer that was fast enough to do that, right? And that required using these things called FPGA, field programmable gate arrays, which is a way of implementing electronics that is much faster. But unfortunately, you cannot use C code. You need to program it, right? It's like programming firmware, and that's which is not very flexible in terms of making changes, but it's much faster. So trying to make it run very fast, right? And then make sure that it was successful. I mean, think about it, right? You're taking an image and then you're trying to compare with a map, right? So you need to predict all the, if you did the map incorrectly with the wrong illuminations or errors, geometric errors, right? Either you're not going to be able to recognize where you are because the image that you take doesn't look like anything, or it's gonna give you the wrong place, right? And so the green zones where you can land, there were no green zones. We have a map with different colors, essentially. That's a green, red. The red was dangerous. Green is super not dangerous. But the smaller the error on where we knew we are, there was more green to be found, right, in the area. It was a series of challenges, I would say, and And yeah, but the other one is that you know until you don't try, you don't know. So
Yeah. For young engineers like me, what's a skill or a project that would prepare someone like me to contribute to future EDL or GN&C systems?
what's it? I'm sorry, can you repeat that again?
What's a skill or a project that would help prepare someone like me in the future for future EDL or
Uh-huh.
GN&C systems?
Well, you know, if I look at the team, right, and I see, you know, we all came from different angles and different journeys, right?
Yeah.
So there are many ways, right, that you get. There is a constant, by the way, which is we all got inspired by the people that came before us, right? So for me, it was Viking. Viking was the mission that you know that inspired me to do what I'm doing today. It's just that's what I want to do, right?
Yeah.
And then you know with Pathfinder, what was the first mission that I worked, right? Uh, with EDL, which was actually the next one that followed. But there was 20 years, nothing happened in Mars. Um, I get to do that one, right? And then I had people that told me, right, that are now my colleagues in the current missions. It says, look, I saw you jumping in that control room, uh, you like the Pathfinder team, so I wanted to do that, right? So I've seen several iterations of that, right? So that's the first thing, right? Is to that inspirational moments. That's what I want to do. How you get there? I was obviously the more prepared, the more you know, good grades, good universities. It doesn't have to be necessarily all, you know, all MIT, Stanford, you know, stuff. I mean, we have people from all, you know, different colleges, right? Um, but they're all, you know, they all work very hard through college and they have very good grades. Yeah, I don't know
Okay.
any people that haven't, to be honest.
Okay.
They have a passion for what they do. I can only speak for myself. I part of because I'm a curious person. I spent more time doing my master's and I took more courses. And having had an electrical engineering degree at undergraduate, right? Actually, I also went to a technical high school.
Okay.
Uh, um, I had a very broad set of skills. You know, I understand a little bit of electronics, a little bit of software. So I can have and also physics, you know, a good background in physics and mathematics is always going to help you, right? So that allows me to have, I'm a G and C person, gas navigation and
Yeah.
control person,
Of
but I can
course.
talk to a mechanical guy, like for example, with the sky crane. The sky crane was an invention that required both mechanical and gas navigation and control. You know, it was a multidisciplinary invention. You could not have G and C guys, you know, invented. You could not have mechanical engineers invented. You needed both to be talking to each other, right?
Yeah.
So that's where the greatest idea happened, interception of two disciplines that sometimes they don't even talk, right? So, but I have the tendency to do to talk to other people from other disciplines because I'm curious, right? And I and I'm not concerned that you know I'm going to sound stupid or anything, right? I prepare myself. I study, I read a little bit, and then I go out and say, well, you know, I know that is not my field, but why don't you do it this way? You know, and many times they say, oh, you know, I never thought about that. So you can bring another
Yeah.
perspective. So that was my, you know, that's the way I, you know, now you have to have a moment of the luck of being able to be in the right place at the right time. For me, that was Pathfinder, right? I was at the right place at the right time. But then given the opportunity, I was able to go with all these tools of you know, and the more you can help in different areas and make yourself useful, then it becomes a virtuous you know system where they then the next mission they hire again, and then the next mission they hire you again. So but the most important thing is that you find the stuff that you make that that you're good at. It makes you're not doing yourself any favor, you know, to pick something that you're not good at, you know. I love music. I would have been a terrible musician because I just, my brain is not wired properly. So I'm just now a consumer. I'm fine with that, right? And and then within the engineering, which is where I do have, an advantage over other people. I was born with that. But even within engineering, I needed to find a place where that I was the most useful. There are certain areas of engineering that I'm not, right? But it just happens to be that the areas that I'm good at, I'm also the one that I like doing, right? So you need to find both, right?
Of course.
And the other thing that that I would recommend, I never thought about doing a career, right? I never say, oh, I need to do this in order to get to this, to get to this, to get to that. I didn't plan it that way. Other people do that with their lives. For me, was what is fun to do now, or the next year, and be the best I could be doing that. And that opened the doors. I didn't have to go figure out what doors to open. The doors just open, right? So those are the advices. So the main thing is find something that you really love doing and that you are good at.
Okay. Yeah, that's great advice, Mr. San Martin. And one of the things that I feel like a lot of these people that I've talked to, including you, kind of stress is that intangible skills like communication and kind of having people skills and soft skills is can be really helpful in the future engineering world. So that's definitely one of the things that I'm trying to get better at in the future. So I can kind of be a strong person, be a strong leader. And that's I feel like is an important thing at NASA, not only NASA, but at
Oh,
many
absolutely.
aerospace companies.
You nail it. It's absolutely true. Um, growing up, right? I love all the classes associated with math and physics and
Yeah,
engineering, and to be honest, I hated anything associated with in my case Spanish, or literature. I just that was not my
of
and
course.
and I always rationalize it like saying, well, I don't need to know to be a great writer or great orator if I'm an engineer. But that's wrong. That's absolutely wrong. It's true. I mean, there are certain engineers that they have a niche where they are in front of a computer and they don't need to communicate. They communicate with formulas.
Hmm.
If you want to be that engineer, probably you can get away with not, with not great soft skills. But if you want to be an architect, which is what I like to architect systems, uh, you know, and bring all these different elements, mechanical, software, GNC, right? Then be able to communicate properly, precisely, um, is fundamental, and somehow despite the fact that I put zero effort in my education to try to make sure that I was that way. It just happened to be actually pretty decent. I discovered that later on in my, when I was in college and writing things, and my wife would look at them. She's a literature major. And then and I said, oh, that's not that bad. And I would go like, really? And but that was very important, and being able to communicate, very precisely, right? Because when you have a vision, you're going to be able to communicate it, to other people so they can implement your vision, right?
Yeah.
Also to try to convince people that's the right thing to do things, right? So, oh, absolutely, is fundamental, and it's very sad that when you see people that are super bright, super, but they just cannot get a concept out, you know, um, and it slows you down sometimes because you need to try to anticipate what they're thinking. They just cannot put it out. That's a problem.